In this video, we're going to look at one-to-one functions and inverse functions. And the objectives we'll focus on are these. One, to determine whether a function is one-to-one. Determine the inverse of a function defined by a map or an ordered pair. Obtain the graph of the inverse function from the graph of the original function. And find the inverse of a function defined by a function. So first of all, you have to know what a function is. And a function is such that for every x there is just one y. So here I have a coordinate system and I have a red line here going through the origin. That would be a function. Now you can try the vertical line test. It tells you if a vertical line crosses a graph in one point only, then that graph represents a function. So here, this vertical line here crosses a graph of this line at one point only. Go over here, for every x there's one value of y. So this is a function. Any slanted line, horizontal line will be a function. A vertical line will not be a function. Because if I consider, say, this graph of this vertical line, when x has this value right there, let's say that's 2. So this would be the graph of, say, x equal to 2. When x is 2, y can be 3 or negative 3, 4 or negative 4, and so on. So a vertical line is not a function. A circle, for example, is not going to be a function, because when I pick x, let's say the coordinate system goes like that. When x is this value, there's two values of y. A one-to-one function obviously is a function, such that for every y, there has to be one value of x. So a function is such that for every x, there's only one y. If it's one-to-one, for every y, there has to be just one x. So here we have the first example. Determine whether the function is one-to-one. So this is supposed to be a function is represented by ordered pairs. For every value of x, there's one value of y. So it's a function, but is it one-to-one? All you have to do is look at the values of y. So notice here, y is negative 1, y is negative 1 here. Now for this ordered pair, when y is negative 1, x is 1. For this one over here, when y is negative 1, x is 2. So there's two values of two values of x when y is equal to negative 1. So these two pairs right here disqualify it by being one-to-one. It is a function, but it's not a one-to-one. So this is no. Now this one says find the inverse of the one-to-one function. Now for the inverse, basically you have this. If you have an ordered pair xy, and they say this belongs to some one-to-one function. So let's suppose this is 1 to 1. For every x there's one value of y. For every y there's one value of x. So it's going to be a function first, and then if for every y there's one x, it's 1 to 1. So if you have an ordered pair xy belonging to this, then if you reverse this ordered pair, make it yx, then that ordered pair will belong to the inverse. And we denote the inverse of the function, of the one-to-one function, by just putting a negative 1 here. And that's not an exponent. That represents f inverse. This is for the function f, the one-to-one function f, and this represents the inverse. If I reverse the ordered pairs, I get the inverse. So that's all you have to know. You reverse the ordered pairs of the function, of the one-to-one function, because remember, it doesn't have an inverse. A function will not have an inverse if it's not one-to-one. It'll have an inverse relation, but it won't be a function. So if they give you the ordered pairs, the second one, find the inverse of the function. In this case, you can see it does qualify for every x, there's one y. For every y, there's one x. So all you have to do, if they give you this situation, is just reverse the ordered pair. So 2, 1, 2, negative 1 becomes negative 1, 2. 3, 2 becomes 2, 3. 1, 3 becomes 3, 1. And 5, 0 becomes 0, 5. So if you call this f, then f inverse will be represented by this. Just reversing the ordered pairs. Now if you're given the equation, let's say you're given y equal to 2x plus 1. And if you noted this by y, I could have said f of x. So if they give it to you as f of x, for this process you want to make it a y. Easier to substitute. So again, based on what we said, if you're given a one-to-one function, this is a slanted line, so this is one-to-one. You simply reverse the ordered pairs. Now if you're given the actual equation of the function, that's the same thing as just interchanging the x and y. So we have a y, put an x. We have a x, put a y. If they give you the ordered pairs of the one-to-one function, and you want the inverse, just interchange the ordered pairs. Now if they give you the equation, interchange x and y, and then solve for y. So here I'm just going to solve this for y. So isolate the y term. So bring this over. 1 goes over, so it's just 2y. And I just divide by 2. So this cancels out here. So the inverse then is y is equal to x minus 1 over 2. This would be, if you use functional notation, you could denote this one as f inverse. And this would be f of x. So notice, if I pick x to be 1 on the original one, the original function right here, x to be 1, and I put 1 there as a 2, and this could be a 3. I pick x to be 0. So notice, if I switch those around, 3, 1, like this, a 3, 1 over here, and a 1, 0. So if I know these 2 points belong to the graph of this line, if I reverse those points will be on the graph of the inverse. So notice if I put a 3 there, 3 minus 1 is 2, 2 divided by 2 is 1, it checks. Put a 1 there, 1 minus 1 is 0, divided by 2 is 0, it checks. So that if I sketch the graph of these, another property that's important is if you have a function and its inverse and you graph them, they're going to reflect over this line of symmetry. They call it the line of symmetry, which is in this case, this is y equal to x. So let's look at the original function. So go 1 here and then 3 up. And then 0, 1 will be here. So this will go something like this. Let me use an actual line here. So that line would go there. This will be half. And then if I do the graph of the other one for the inverse 3, 1, 1 will be there. And then 1, 0 would be here. So you have something like this. And this is not the scale, so it's a little bit off, but the graph of f, this would be f here, and this would be f inverse. They should be symmetrical around that line. My graph's a little bit off though, but that's what you would have. This point should be over here a little bit. But that's what I'd function f and its inverse having function. They're symmetric about this particular line here. Let's clear this, and you'll see this a little bit clearer in the next one. So for the graph shown, draw the graph of the inverse. Okay, so this is f. And they give you the line of symmetry. So there should be a point somewhere over here. This point, say that's 0, 1, this should be 1, 0. And if you reflect this graph over that line of symmetry, so this is the line y equal to x. Or like this. This actually comes down a little bit more this way, but it's right in here. So if they give you the function, the one-to-one function, and they want the inverse just reflected over this line, now if they give you the inverse, the graph of the inverse, and you want to represent the graph of the function, again, just reflect it over the other side, and you get the function, or the graph of the function. Let's look at the next one. For the function f of x equal to x squared minus 2, x is greater than or equal to 0. So here they're actually telling you the domain of the function, x greater than or equal to 0. State the domain and range of both functions and graph the function as well as the line, as well as the line y equal x. So let's do this first. Let's call this y, and we're going to interchange x and y. So this is going to be x. Where I have a y, I put an x, and where I have an x, I put a y. And then I just solve this for y. So this will be, let's add 2 to both sides. I get y squared is equal to x plus 2. I take the square root of both sides. And because the x is greater than or equal to 0, that means the y has to be positive here. So I take the square root of both sides. So I only take the positive square root. The square root of y squared is y, and this will be x plus 2. So what you have to keep in mind is the domain of the function is going to be the same as the range of the inverse. So that's why the y has to be greater than or equal to 0, so this has to be a positive square root. So there I can denote this then as f inverse, and that will be the square root of x plus 2. Good, so let's look at the graph of these. The graph of the original function, x squared minus 2, is a parabola with vertex at 0, -2. Now the line of symmetry, y equal x, is this. We go like this. I added on the other one. So the line of symmetry there is in red. And in the graph of the parabola, the original function goes down, vertex at 0, -2. So this is a parabola that goes this way. It goes like this and then up. But because the domain is greater than or equal to 0, we only want the right side. So instead of doing this graph this way, we take this graph here. It goes like that. So that's f. So the graph of the inverse we reflect it over this. So this one would go, this is 0, -2, so it would have to be over here, -2, 0. So this one then would go something like this. This would be f inverse. And then what's the domain of these? So the domain of the function, that's given. But you can see from the graph here that the function stays to the right of the y-axis, so x has to be greater than or equal to 0. So the domain of f goes from 0 to infinity. And again, just remember that the domain of the function is the same as the range. So this is the same as the range of f. And you can see that function f, this is f inverse here, stays above the x-axis, so that's 0 to infinity. And then the range of the function, you just look at the graph of the function, that's the value of the y, so that's from -2 to infinity. So this is going to be -2 to infinity. But that's the same thing, that should be the same thing as the domain of the inverse. Because you can see where the x value of the inverse starts at -2 and continues to the right. So it's everything greater than -2. So it's -2 to infinity. So that's the domain of the range of the function and the inverse. Let's clear these. And then in the last one is find the inverse of the function. And this is a one-to-one function. So again, let's call this, instead of f of x, just to make it easier in the substitution, let's call that y. And then we interchange the x and the y. So I have a y, I put an x. Where I have an x, I put a y. So again, replace the y by x and the x by y. And then we just solve for y. Those are the steps. Anytime they give you the function, the actual equation for the function, interchange the x and the y and solve for y. So here, let's just clear the fractions first. Let's multiply through by 2y plus 1. multiplying both sides by 2y plus 1, so it's going to cancel on this side. 2y plus 1. This side, here it is, and then here this cancels. So this just gives me y. And then here we just multiply through by x, so this will give me 2x y plus x is equal to y. And then we're solving for y, so we want the y's on one side, everything else on the other side. So let's bring this y over to this side. It just changes the sign. So this will be 2x y minus y. And then you take the x over, that's minus x. And then we're going to solve for y, so let's factor out a y from this one. So I'm going to take out the y here on the left side. That'll give me 2x minus 1. So I got y times 2x minus 1 x, and then I just solve it for y. So I divide both sides by 2x minus 1. So this will give me on the right side minus x over 2x minus 1. And then you can rewrite this as, if you want it in functional notation, this is actually the inverse. So it'd be f inverse of x, and that's equal to minus x over 2x minus 1. And depending on what you did, it could turn out that this is positive on top, and this is minus 2x plus 1. Either one is correct. So there you have it. Thanks for watching. We'll see you next time.